So we ended with preparing solutions from other concentrated solutions. So you take something that's really concentrated and you take a small amount of it and then fill the rest with water. And that's so you now know two types of ways to prepare solutions. So now what we're going to do is we're going to do some good old stoichiometry. So remember, stoichiometry is just how you jump around with mole ratios in a chemical reaction. And you learned how to do this last year. So generally, we would start you out with grams. You would turn grams into moles, and you'd be able to do mole to mole ratios. And so we're going to do this now with solutions, but we're going to have a different starting point. So instead of grams to get us to moles, we're going to use molarity and volume to get us to moles. Because remember that the equation for molarity is sorry about that. Molarity equals moles per liter. So if you know molarity and you know volume, you can get moles. Once you're in moles, you can do stoichiometry. So it's just going to be a new starting point. Everything after that is going to be the same. So let's try a practice problem. It says some metals will react vigorously with acids to produce hydrogen gas. What mass, now remember mass means grams, what mass of zinc, so I want mass, so this is grams, of zinc metal will react completely, and then I give you a volume and a molarity. Remember, this means moles per liter sulfuric acid. So molarity and volume can get me moles. Now, the first thing you need to do, though, is write out a chemical reaction. So we'll do this one together. Zinc reacts with sulfuric acid. Okay, this is single replacement. Zinc is +2, sulfate is -2, so they go together nicely. Okay, and we get the bubbling of the hydrogen gas. And now let's look at the problem. So they say they want mass of zinc, so they want to know about this guy. But all of the data or numbers that they give you is for this guy. So if I want to talk or answer questions about zinc, I'm going to have to be able to jump from my data of sulfuric acid over to zinc. And the way you jump around in a chemical reaction is mole to mole ratios. Now you can't do mole to mole ratios unless you are in moles. But the molarity and my volume will allow me to get moles. So 0.200 moles per liter times, remember this has to be in liters, 0.075 liters. What does that get us? How many moles? So this is 0.015 moles of, now remember these two numbers belong to sulfuric acid. So now I'm in moles. So like before you had this class, the way you got to moles was from grams. This is just a new method that allows us to get moles for solutions instead of grams generally refers to things as solids. So I have my moles of sulfuric acid, and then I look at my reaction. I go, okay, for every 1 mole of sulfuric acid that react, 1 mole of zinc reacts. And I wanted grams though, so 1 mole of zinc is, jump to your periodic table, you find zinc 65.38 grams. Sorry about running out of room. And you take and you calculate this out, 0.015 times 65.38. This is a 3-digit number and this is a 3-digit number, so your answer should be 3 digits. And this is the mass of zinc you would need to react completely with this much acid. Any questions so far? Okay, let's try another one. So I want you to try this one on your own, but I'm going to start you off first. So it says, what mass of calcium carbonate is required to react completely with 25 milliliters of 0.75 molar hydrochloric acid. So they want grams of calcium carbonate, and they give you information about hydrochloric acid. So the first thing you need to do is at least write out your balanced chemical reaction. So I want to give you a second. And can anybody tell me who the products are?
Calcium chloride, water, and carbon dioxide.
Very, very good. Remember, this is a carbonate with an acid. So this is a special type of reaction. Calcium chloride, water, and CO2. Carbonates with an acid will give you salt, water, and carbon dioxide. So now I have to go ahead and balance it. So there's a 2 in front of here. That gives me 2 hydrogens and 2 chlorines, 2 hydrogens, 2 chlorines, 1 calcium, a carbon, 1, 2, 3 oxygens, 3 oxygens. Okay, so this is balanced. Now, they gave you information about hydrochloric acid, but they asked you about calcium carbonate, meaning I'm going to have to jump from here to here using mole ratios. So I take my molarity and my volume and I get moles. So I'm going to do this down here. 0.75 moles per liter, that's what molar means, times 0.025 liters gives me 0.01875 moles of HCl. Both of those numbers belong to my hydrochloric acid. Well, now that I'm in moles, I can do stoichiometry or mole ratios. So 2 moles of HCl and 1 mole of calcium carbonate reacting. Sorry, I ran out of room. Let's see if I can do it over here real quick. It's a 2-to-1 ratio, right? And then you'd say 1 mole of calcium carbonate has a certain molar mass. I'll look it up for you guys. 100.09 grams per mole. So 0.01875 divided by 2 times 100.09. Oops. I did mess this up. So this is 2 sig figs, this is 2 sig figs, so this should be 2 sig figs. So the answer should be 0.94 grams of calcium carbonate to react with this much acid. So again, this isn't really much different than the stoichiometry you're used to doing. You're just getting moles in a different method, and then the rest is the same, mole to mole ratios and then moles to grams. Our starting point is different. We have a molarity and volume starting point instead of a grams starting point.
I have a question.
Yeah.
Wait, so why does it break into H2O and O2?
It's the way that carbonates react with acids. Carbonates and bicarbonates tend to do this.
Okay.
It's one of those special reactions that is not double replacement like it looks like.
Okay, so it's always just when there's carbonates.
Carbonates and bicarbonates with any acid will break apart into salt, water, and carbon dioxide, yes.
Okay, thanks.
You're welcome. All right. So when aqueous solutions of potassium iodide and lead 2 nitrate are mixed, a precipitate is formed. So I would like you to take a moment and try to write out the reaction and predict the products and discover who the precipitate is before we do anything else. So potassium is +1, nitrate is -1. So they go together nicely. Lead is +2, iodide is -1. So I needed 2 of the iodides, and then we balance like this. And then how do you know who the precipitate is? Well, the reason you know who the precipitate is because you have to memorize that alkali metals, or there's another rule, nitrates are always soluble. So by default, this guy is soluble, which makes this guy your precipitate. That's how they can ask you to know who the precipitate is, because one of the products will be one that's generally always soluble. Okay. Now, before we move on, I want you to read what they give you. So they want you to calculate the mass of the precipitate. So that's this guy. And then they give you a molarity and a volume of the lead 2 nitrate. So that's this guy. And they also gave you a molarity and a volume of the potassium iodide. What type of problem is this, and how do you know? Anybody remember? No one? It is limiting reactant. Thank you, Micah. Limiting reactant. Okay, how do you know? What is your hint that it's a limiting reactant? Well, they gave you amounts of both reactants. And the prior problems, I only gave you one substance and we found another substance. Because I have two substances present and amounts of them, it's highly likely that this is going to be a limiting reactant problem. So what do? Well, we have to find the moles of each reactant. So molarity times volume is moles. So I'm going to do the potassium iodide first. So 0.0250, moles per liter times 2 liters. So this is 0.05 moles of Ki. Okay, and then I'm going to do it again, but I'm going to do it for the lead 2 nitrate. So 0.05 moles per liter times 1.25 liters, right? These liters cancel. This ends up being 0.0625, I think. Oh, let me double check. Yep, okay. Now, here's where you have to be careful. You do not instantly get to pick the lowest number for your limiting reactant. You have to consider mole ratios. So I know in Excel Bio they taught you to do stoichiometry with both reactants, and whoever produced the least amount of product was your limiting reactant, okay? And that's fine. You can totally do it that way. I'm going to show you my way that I kind of cheat. In essence, I'm doing what you're doing, just in kind of a shortcut version. And I'll show you how I do it, but you are totally welcome to do the other way. So what I do is I look at my moles right here of potassium iodide, and I divide by its respective coefficient. So there's a 2 in front of it. And then I do the same thing for my lead 2 nitrate. So lead 2 nitrate, there's a 1 in front of it, so I would divide by 1. Whatever number comes out to be smaller is your limiting reactant. So 0.05 divided by 2 is 0.025, which is definitely smaller than 0.0625. So the potassium iodide is my limiting reactant. That means I don't even care about my other substance right now. The limiting reactant is going to determine the mass of the precipitate. So I take my, my moles of my limiting reactant, and I say, okay, for every 2 moles of potassium iodide that react, 1 mole of lead 2 iodide is produced. And 1 mole of lead 2 iodide. This guy's pretty heavy. I'll look it up. The molar mass from the periodic table is 461 0.01 grams per mole. So 0.05 divided by 2 times 461. Now for sig figs, you use whoever's number you did math with. We did the math with potassium iodide's number, so these are the only sig figs we focus on. This is 3 and this is 3, so your answer should be 3. 11.5 grams of lead 2 iodide theoretically should be produced. Questions?
Where did you get the 2 from when you divided by the 1 and the 2? Where did you get the 2 from?
This one? Right here?
When you divided 0.50 moles and...
The 0.05 moles was for potassium iodide. You mean how I picked the limiting reactant?
Yeah.
The 0.05 moles of potassium iodide, so potassium iodide is here. So you take this number and you divide by its respective coefficient,
okay.
which is a 2.
Thank you so much.
And then the lead 2 nitrate, I divided by a 1 because there's really an invisible 1 in front of it. And that's how I quickly determine my limiting reactant instead of doing stoichiometry with both of them. Because look, in essence, that's what you end up doing here. Look, you do end up dividing by 2.
You do.
It's just a shortcut method. Good question.
Thank you so much.
You're welcome. Are there any other questions? Okay, let's keep going. All right, so this is an actual picture of this reaction. So notice you'll see that this aqueous solution right here has lead ions and nitrate ions floating around, right? Lead 2 nitrate, they're just floating around in solution. You can't see them. It's a totally colorless solution. And then potassium iodide, that's this solution right here, is potassium ions and iodide ions. This is what it means to be aqueous, that the substances float around as ions in solution, aqueous. And then notice when you actually mix them, you see this yellow stuff that gets produced.
Have fun.
Love you.
Learn something.
Gosh. This yellow substance that gets produced. So this is your lead 2 iodide. This is your precipitate. And when you give it a chance to settle out, you can see the solid sitting at the bottom. Notice how they show you the solid all kind of lined up together, sitting at the bottom. And then you got your spectator ions sitting on the top of here. That would be your potassium ions and your nitrate ions. So technically you could separate this out. You could filter this out. You have to filter this out, get rid of the solution on top, and then the filter paper would collect the precipitate, and you could then dry it and mass out the precipitate. Are there any questions about this? Okay, so let's try another one. So a sample of potassium phosphate is added to silver nitrate, resulting in the formation of a precipitate. So write out the reaction. So take a second to do that, please. See if you can write out and predict the products of the reaction. Potassium is +1, phosphate is -3. Silver is +1, nitrate is -1, so they go together perfectly. So this is a classic double replacement reaction. So the potassium is going to pair up with the nitrate and the silver is going to pair up with the phosphate. Well, potassium is +1 and nitrate's -1, so they pair up perfectly. And silver is +1 and phosphate is -3, so. And then again, how do we determine who the precipitate is? Well, nitrates are always soluble, also so are alkali metals. So potassium nitrate is my aqueous solution. So by default, that makes the silver phosphate the precipitate without having to know the other solubility rules. So I have to balance. Let me balance. Let's see. I need 3 potassiums, which gives me 3 nitrates. So I need to put a 3 here, which gives me 3 silvers. 3 silvers. Questions so far? Okay, I recognize that part B asks you who the limiting reactant is. But if I didn't, if I would have dropped this part B and went straight to part C, how would you have known? I'm trying to teach you strategies, right? Trying to figure out how to start problems and knowing where to go is one of the hardest parts of this class. How would you identify that this is a limiting reactant problem? What gives it away that it could possibly be a limiting reactant problem? What's like a sign?
When it says resulting in the formation of a precipitate.
Okay, so we are going to form a precipitate, but there is another way that we're going to know that it's a limiting reactant problem. Anybody? So you want to get good at this. What is the hint that this is a limiting reactant problem besides the fact I told you? Pretend that's not there. How would you recognize that this is a limiting reactant problem?
It gives you two of the reactants.
Okay, it gives you amounts for both reactants. That is the biggest hint that it's a limiting reactant problem. When you have both reactants, it's almost always a limiting reactant problem. So this is kind of interesting. They gave you the mass of potassium phosphate, which is like the old way of how we found moles, right? You have to turn this into grams and then grams into moles. And then for the silver nitrate, they gave you molarity and volume for you to be able to get moles. So let's do that. Let's find the moles of potassium phosphate and let's find the moles of silver nitrate. In order to figure out who the limiting reactant is, you have to be in moles. Why do you have to be in moles? Because these ratios, this 1, 3, 3, 1, are called mole ratios. They're not gram ratios. So you have to be in moles if you want to compare them. So let's find the potassium phosphate first. So I'm going to rewrite that as grams. This is 0.0705 grams of potassium phosphate. And we got to turn grams into moles. And I have no idea what that guy's molar mass is, so $212.27. So this is 0.0705 divided by 202.27 is 0.00033-ish moles. Okay. And then we need to do this again, but we need to do it for silver nitrate. So the way we get moles for silver nitrate is molarity times volume is moles. So 0.050 moles per liter times 0.015 liters. Then our liters cancel, and we're left with moles. Here the grams cancel. So 0.05 times 0.015. So this is 0.00075 moles. Okay. Now, can I just go, oh, look, potassium phosphate, this number's smaller, so it's my limiting reactant. Can I just do that instantly?
No.
No. Why not? What do I have to consider?
The different moles, different amounts of moles.
Good, the different mole ratios. So I'm going to do my cheating way. So I'll repeat again how I do it. This number belongs right here. This 0.0033 belongs to potassium phosphate. There's a 1 mole in front of it, so I would divide this guy by 1. And then silver nitrate, there's a 3 in front of it. This number belongs to silver nitrate, so I divide by 3. Uh-oh, when you divide 0.00075 divided by 3, you get 0.00025. That number is smaller than 0.00033. So your silver nitrate is your limiting reactant. Questions so far? So what do you do now? Well, who cares? You don't care about anybody else but the limiting reactant. So let me erase all this. So you take your limiting reactant, 0.00075 moles of silver nitrate, and you do all of the math with it. You say for every 3 moles of silver nitrate that react, 1 mole of silver phosphate is produced. Wow, this is like not writing very well. Okay, and 1 mole of silver phosphate is, I have no idea. I'll have to look at the molar mass. $418.58. 418.58 grams per mole from the periodic table. So you take and you divide by 3 and then you multiply by 418.58. Now, sig figs. We used silver nitrate's numbers. So sig figs are based on silver nitrate. This is 3 sig figs, this is 2 sig figs, so your answer is 2 sig figs. 0.10 grams of silver phosphate will be produced if you have this specific situation. Questions? Okay. All right, so guess what? You're going to do a precipitation multiple choice question, limiting reactant problem without a calculator. How crazy is that? Okay, so I give you the balanced reaction, and then the problem gives you molarity and volume of silver nitrate and 0.540 grams of aluminum. So you have both reactants, which is your hint that it's a limiting reactant problem. And they want to know what's true. So in order to figure out what's true with all of these answers, we need to start doing the math. So we need to like get into moles of each substance before we can even answer any of these questions. So let's find the moles of the silver nitrate. Well, silver nitrate. So 0.80 moles per liter times 0.1 liters. Now, if you're like me and you're not very good at decimals, I do this. 8 times 1. So like I make the numbers easier. 8 times 1 is 8, right? But then this wasn't really 1. I have to go backwards 1 spot to get to my original decimal, and I have to go backwards a 2nd spot. So 0.08 moles for the silver nitrate. Okay, now we're going to do this again, except for they gave me grams as my starting point for aluminum, so you should be able to use the periodic table to turn grams into moles. So you go to your periodic table, and aluminum is 20, like we don't get a calculator, right? So like right at 26.98 is 27, pretty much. No calculator, so 27 grams per 1 mole. Now, again, I can easily divide 54 by 27. It's 2. 54 divided by 27 is 2, but I got to technically go backwards 2 spots, so go backwards 2 spots. So it's 0.02 moles of aluminum. Okay? So the first 2 answers have aluminum as the limiting reactant. Let's figure out if it is the limiting reactant. So 0.08 moles of silver nitrate divided by 3, right? Because there's 3 in front of here. So you would divide this by 3. And then there's a 1 right here. So 0.02 would be divided by 1. This number is still bigger than aluminum, so aluminum is your limiting reactant, so I can't throw out A or B yet. Okay, well, if aluminum is my limiting reactant, so 0.02 moles of aluminum, and aluminum nitrate are in a 1-to-1 ratio, you would get 0.02 moles of aluminum nitrate produced. This says 0.04. So it's out. It's wrong. And this says 0.08 moles of silver are produced. Well, for every 1 mole of aluminum, there's 3 moles of silver. 0.02 times 3 is 0.06, not 0.08. So that one's out. Questions so far? All right. Both A and B are discussing excess. So now we're going to have to figure out the excess reactant, which is silver nitrate. So you say, okay, I'm going to do stoichiometry, 0.02 moles of my limiting. And for every 1 mole of aluminum that reacts, 3 moles of silver nitrate react. 0.02 times 3 is 0.06, 0.06 moles of AgNO3 that react. Well, how much did I start off with? Well, I started off with 0.08 moles, right? So if you had 0.08 moles to begin with, and 0.06 moles react, you have 0.02 moles left over. So B is your answer. Whew. And without a calculator. Do you have any questions?
In the last part, why does it say 0.08 in red?
This is how much you had initially.
And then you have the excess product. Okay.
Yep. So this is how much silver nitrate we have at the beginning of the reaction. This is how much reacted. So the difference between them is how much is left over. Good question. Are there any other questions? All right. So that is where I'm stopping for today. So here's how I want test corrections to go. So at the top of the page, you'll write chapter 1 through 3 test corrections. And then you will write down the question that you missed. So you'll write like, I missed number 2. So you'll do number 2. You will write out the full question, whatever question number 2 is. And you'll draw a diagram if there's diagrams. And then you will put the correct answer and why it's the correct answer. So like if there's math or a work that you need to do with it, you will include that. If the answer is self-explanatory, like and sometimes it'll say, this is like an explanation, then you don't have to do anything else but write the correct explanation. So you write down the question that you missed, and the correct answer, and you don't do any of the ones that you got correct. Okay, the ones you got correct, you don't have to worry about, and then you're going to submit it as test corrections. So we have a decent amount of time left in class, so I'm going to let you work on your test corrections. I'll be hanging out here because I'm sure you'll have questions. There are a couple of common questions that kids had that were kind of missed across the board, but feel free to hang around and ask questions, or you can leave and work on them on your own and hop back on in a little bit if you want. The other thing I want to tell you is that your homework, some of your homework problems have what are called ice charts. And you don't need to know how to do those yet. So just skip the problems that talk about ice charts. You can do the other ones, but just skip those problems. And yes, please explain what, I don't need you to explain why you got it wrong. I just need you to know why the answer is the right answer. I don't want to know why you got it wrong. I want you to understand why the right answer is the right answer. So like, for example, the Kelvin problem, the one that says 10 degrees Celsius to 20 degrees Celsius and asks for change in Kelvin, you should show the math for that. It's still a difference of 10 Kelvin when you subtract them. So something like that you would show work for. The other big one kids missed was the word indivisible in Dalton's postulate. He had said that atoms were indivisible, meaning they can't be divided further down, and we know that's not true because atoms can be divided further down into protons, neutrons, and electrons. So again, I'm going to hang out on here and answer any questions you might have and work through any answers you might have. Right now it's just time to ask me questions about the test and work on your corrections or start your homework. And other than that, that's all I've got for you for today.